Yeah, so ESCO was going to do this, but I'm here instead. But that's okay, because we've both been working on this together. Although credit to ESCO for much of the implementation work, because he and I have been working on this together. So,
if there's any way you can get the microphone closer to your face, that'd be a good idea.
Okay.
Hook it over your ear.
It's just wind you ahead of it.
I think you broke it.
Can I just say,
Yeah, that works.
All right. Thank you. Right, so I want to start this. So I want to do a very quick recap on Cloud Haskell, just because you might not have seen it since last year. But I'm not going to go into lots of detail now because I won't have time to talk about all the cool new stuff if I do that. So I'm going to tell you a bit about the details of the new implementation, and some stuff to do with semantics, and then a little bit about the current status. And this isn't a tutorial, this is the grungy internal details. But if you want a tutorial, I will be doing one next month in London. So a very quick recap on Cloud Haskell. So the slogan could be Erlang for Haskell, but as a library. So it's explicitly concurrent, and it's all about distributed concurrent programming, and it's both a programming model and an implementation. Now, two implementations of this model. So the point of this thing is to let you program clusters. So this is distinguished from just using your normal client-server socket programming. The idea here is that you're programming a whole bunch of nodes as one. You're running one program across an entire collection of nodes. You're thinking of it as one program and just lots of resources available to you, rather than kind of in one little box, just thinking about what comes in and out of the one node. So this is based on stuff by Simon PJ last year, presented last year. Jeff Epstein, who co-authored the paper and wrote a prototype implementation. And this is what he did for his MPhil thesis. So the programming model, as I said, is explicitly concurrent. This is the actual model. Now, you may not have used it, but I think most of us are sort of vaguely familiar with what it is because people talk about it so much. So this is the actual model. It's the same thing that Erlang and what Cloud Haskell does. So these lightweight processes, a synchronous message passing between processes, and no shared state, so that you can actually distribute them. So the basic approach of Cloud Haskell is that the design is such that it can be implemented as a library. This is one of the key breakthroughs in design. So it doesn't require lots of runtime system modifications. In fact, it doesn't require any runtime system modifications. And the other sort of part of the design principle, if you like, was, if in doubt, do it the way Erlang does it. And other middleware designs, other distributed middleware designs are possible, like we saw HDPH mentioned earlier, and Metaply. So this is in the same kind of area. So the core API, this is the thing you probably want to pay a little bit more close attention to, because we'll talk about some of these primitives a little later. So we have a process monad, and it can do arbitrary I/O, but the distributed stuff happens in the process monad, not in I/O. You've got process IDs. Processes live on nodes, so a node, just think of it as a machine. So you have node IDs to which address these nodes. You can think of those as being like network addresses. And you can send, a process can send any message to another process, so long as it knows the process ID and the thing it wants to send is serializable. You can receive or expect a message of any type, and if it doesn't match up, then you ignore it. You only receive messages of the type that you expect. You can also spawn explicitly onto a node identified by its node ID, and you pass a closure of the process that you want to run on that node. And that gives you back the ID of the new process that you just spawned. And you can also find out what node you're running on and what your own process ID is. So that's the sort of the core API. You can send and receive, and you can start new processes on new nodes, or the same node. Error handling is also very important for distributed programming, and Cloud Haskell steals Erlang's approach, which is to let processes fail. You simply have to notify people that things have all gone wrong. There's two ways that Erlang has to do that, and Cloud Haskell copies it. One is process linking, the other is monitoring. Linking says, I want to link to that process. If it dies, kill me as well. Monitoring is similar, but not quite so extreme. It just says, if that process dies, tell me. And on top of that, you can build all kinds of systems for making things reliable. So the key primitive is simply you need to know that things have gone wrong, and then you can do something about it. So, Cloud Haskell, that's the basic design, API. So what we've been up to, so after the paper was presented last year, Simon and PJ asked us to start working on a new implementation. And the goal is for the same public API, but to be a more robust implementation and to be a more flexible implementation than the prototype. And we ran into some interesting problems, and I will tell you a little bit about those. So, flexibility first. Why do we want a more flexible implementation? It's because there's lots of use cases. There's lots of different environments in which you have distributed programs you want to run. You've got like a shared memory machine, or like a NUMA machine, for example, and you might want to treat that as if it's distributed memory. You have clusters that have their existing job schedulers, and you have to integrate into those environments. You've got cloud systems, like Amazon and Azure, and that sort of thing. So there's lots of different variations between these environments, and some of the axes of variation is like what network protocol we use. TCP, InfiniBand. How do you start the executable on each machine? Is it done by a job scheduler starting it for you, or is it done by you spawning something on a new node that's been just created? How do you distribute configurations of nodes? That varies between these environments. And how do you actually find the peers? Sometimes you create peers in a VM environment, in a cloud environment, and sometimes your peers are given to you statically. So there's all these variations, and we want to be able to deal with that in a sensible way. So the new implementation is designed to allow for this flexibility. So in particular, we have this swappable network transport layer, and that deals with the difference between TCP and InfiniBand and shared memory. And then we have multiple Cloud Haskell backends, so to help you. Once your system is initialized, it's all the same. But there's one Cloud Haskell API, but to get things set up, the initialization, configuration, finding the peers initially, that's done separately by each backend. And I'll give you two examples of those, because we've got two implementations of backends so far. And another difference between the prototype and what we've been working on is we've been thinking more about semantics, and I'll come on to that. So this is what the sort of block layout diagram of the existing prototype looks like. You've got your application at the top, it just uses the Cloud Haskell library, and it's directly implemented on top of the network package, and it uses TCP. And you could, in principle, have other libraries of MapReduce of patterns and things implemented that just use the Cloud Haskell library, and then those are reusable in many different situations. So our new design is a little bit more complicated, but it's not too bad. Okay. At the top, you've still got your distributed application, and your application depends both on the Cloud Haskell, main Cloud Haskell library, and on one backend. And this isn't so weird, this is just the same way that database libraries work. You've got the general database interface, and you have a specific backend for Postgres or whatever. And your application depends on both. It calls one function to initialize, and then it just passes it off, and then you use the main API for the rest of the time. So this still allows you to have libraries of reusable distributed patterns that don't depend on any backend, and your particular application uses one backend to initialize, and then it should be easier to port from one place to another, from your job schedule environment to your cloud environment by changing the backend and only changing the bit of code that does initialization. Now, next layer down, we've got this network layer. So there's this network transport interface, that's a separate package. So that just defines an interface, nothing else. And then we have multiple packages that implement that interface. And each Cloud Haskell backend picks one implementation. So for example, our very simple backend just picks the TCP implementation of the transport, and then uses that to initialize Cloud Haskell. And each of those different transport implementations can depend on different low-level networking libraries. For example, TCP, or InfiniBand libraries, that sort of thing. So let's just talk a bit about what's happening at the transport layer, and then I'll come on to what's happening at the process layer. So in fact, simply having this transport layer has really helped us to simplify and clarify the code in our implementation. It's now much clearer what stuff is happening at the transport, things to do with network errors, and then higher level things. The code is now much clearer than the code in the previous prototype. So some things we were thinking about when designing this network layer, we were talking to Peter Braun actually at the beginning, and he was telling us that he wants to do this stuff with high performance computing and InfiniBand, and so we have to make we have to think about the possibility of scaling to tens of thousands of nodes, even if our TCP implementation won't do that. The interface has to be such that it could be possible to write an implementation using the CCI library, for example, which does InfiniBand and other HPC network systems. So we wanted it to be potentially scalable, even if the implementations we did initially were not going to be. So yeah, big clusters and low latency. And we wanted to find a sort of common semantics so that it really would be possible to swap different implementations and not have that change, not have that make things go wrong. So the key features of this transport layer is you've got these heavyweight endpoints. So you have like one endpoint per Cloud Haskell node. And then between endpoints, you can have a bundle of many lightweight connections. And those connections are reliable and ordered. You send messages over them, not streams of data. And they're unidirectional, just because that was simpler, they're lightweight. On each endpoint, you have a shared receive queue. So you receive messages from all the connections down in one. When you call receive, you can get a message on any of those connections, and it just tells you which connection ID it was from. And that's an idea that was taken from this HPC networking library. Because apparently, you can read the paper about that, but it turns out that can be quite important for scalability, to have a single shared receive queue. And in particular, this receive queue also contains error events, like all your connections to this node have just died. It tells you that sort of thing. So the errors and the messages are all received together. We tried to pay careful attention to network errors, network failures. So all of the functions in this interface are very explicit about what possible errors can occur. And so each particular implementation has to translate into these common possible errors. And that's what allows the higher layers to deal with network errors in a portable way across these different transports. So in particular, we don't use exceptions. We're explicitly returning enumerations of possible things, and there's a meaning to each of these possible error conditions. And one thing we discovered slightly later, a little minor issue, is that it turns out it's rather important or rather useful to have I say we have these little lightweight connections, and we use those between lightweight processes. But it's rather important to have those bundles of lightweight connections fail together, not fail independently. Failing independently causes no end of headaches, so having them fail together simplifies things considerably. So in particular, we have a TCP implementation of this, and it uses a single heavyweight TCP connection between endpoints and multiplexes lots of lightweight connections over that single TCP connection. And in that situation, the fact that we have a single shared receive queue becomes quite important for avoiding technical issues like head-of-line blocking and such things that network programmers know about. Ryan was working on a pipes implementation, which needs to be updated to our latest iteration of the interface. I think some of Peter's people are working on a CCI implementation.
In fact, Jeff Epstein is.
Yes, right. Okay. So yeah. So Jeff, who did the prototype implementation, he is working for Peter, doing a CCI implementation of this interface. As I said, this is to do with performance computing and InfiniBand and that sort of thing. Also possible in principle, shared memory, so that when you have a cluster of SMP machines and you want to have, and you might want to have multiple nodes on the same SMP machine and use shared memory to talk to each other, rather than having one large shared heap, for example. That might be faster. SSH, I think, would be rather handy because there's lots of sort of ad hoc networks which could use, which do use SSH, and it'd be nice to be able to use a transport over those. So there's these other possibilities, but the ones we've implemented so far is the TCP. Okay, so moving from now the transport layer, moving up to the process layer. So this is the Cloud Haskell layer proper now, if you like. So it's just a very, very brief outline of what this sort of implementation looks like and how does it relate to the transport layer. So you have these nodes, which is, you can think of them as being machines, and nodes are basically where processes run. They're collections of processes, and they manage those lightweight processes. And so in particular, there's one of these heavyweight endpoints from the network layer, one endpoint per node. Each process, each lightweight process, uses a simple Haskell lightweight thread, and it has a queue for incoming messages. There is one of these lightweight connections per pair of processes that are talking to each other. So every time a new process talks to another process over there on a different node, it makes a new lightweight connection, and that's very, very cheap. There's one thread per node to receive all these incoming events, messages, error events, that sort of stuff. And there's also another thread on each node that is the node controller, and that's the thing that deals with the Cloud Haskell Erlang notion of linking and monitoring and spawning. It provides all those services. And there's also one other service for doing this logging. So we've got, I mentioned backends. To start with, we've got this one very simple backend just to get things working. It's similar to the backend, similar to the initialization procedure in the old in the old prototype. It's got no configuration. It uses TCP as the transport, and it uses local broadcast to find peers, which is exactly the same thing as the other prototype did. So that makes it quite easy to start, just to start with going, but you wouldn't use it in a larger situation where you need more control. But it's relatively simple to write these backends. You don't have to, they're very short, so you can write a new one. You don't have to, whereas the network layer is a bit harder to implement, but these backends are quite simple, quite short code in particular. We are also working on a Windows Azure backend. And this is actually rather interesting. It sort of illustrates the fact that having these multiple backends is useful because each backend is doing something rather different, and you can use types that are specific to the situation you're in. So we can use the types of, the Azure. We have a little binding to a part of the Azure API, and we can use, and it's important to be able to use those types of Azure configuration in your program, whereas trying to use some generic, trying to do a generic initialization, a generic configuration, is not nearly as good. Here we can use types that are specific to the situation you're in. So you initialize this backend by giving your Azure account so it can start spending money on your behalf, and your SSL certificates and blah, 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 all that stuff. And then that initializes your Cloud Haskell node, and you can start going. There's some additional features in that backend for enumerating VMs, starting nodes, etc. It's not yet released, but it will be soonish once we get other people to apply some patches. Semantics. So we started implementing this process layer, and then we thought, what's it supposed to do exactly? Now, the original Cloud Haskell paper doesn't really say what the semantics of that message passing are. It just says that, it says message passing is supposed to be asynchronous, reliable, and buffered, but that's sort of all it says. So I was looking at examples like this. What does it do? What does it mean? What properties should it have? Should I expect that this would reliably send the message hi? So okay, what does this do? We link to another process, and then we send it a message, and then we unlink. Should I expect that after I've done that successfully, it had definitely received it? Because by the time I unlink, is there some kind of ordering between these things that would guarantee anything at all? We didn't really know. So, remember our design principle, if in doubt, do it the way Erlang does it. So, what does Erlang do? And we looked around, and it's not that easy to find out what it does. The docs are rather fuzzy, and in some places they're wrong. You can be kind and say they're glossing over details, but some are actually rather important details. But there's a couple of good papers, academic papers, which go into the gory details and explain that it's not quite as nice as we had thought. So, the important questions you want to ask are, well, what is the behavior of message passing? So you've got two processes, and you're sending sequences of messages. Is there any kind of guarantee reliability or ordering? And what does linking and monitoring do? And how does linking and monitoring relate to sending messages? So, what does reliable and ordered mean? Well, networks are always sort of fundamentally unreliable. You can never get anything through. You can't guarantee to get anything through. So what does reliable mean in terms of networking? So there's this property that says, if you send a sequence of messages, the other end will receive some prefix of them. So it might receive nothing at all, It might receive the first message, might receive the second message, but it's never going to receive the first message and the third message without getting the second one in between. That would be unreliable. And the Erlang...
Erlang can generate this, right?
Sorry, say again?
It can happen in Erlang.
I'm going to come to this exactly, yes. So the Erlang FAQ goes through a bit of, goes over this issue, and it sort of summarizes at the end by saying, if you think TCP is reliable and guarantees delivery, which most people do, then Erlang, so is Erlang. Erlang is reliable in the same sense. So TCP does guarantee this property. You're sending a sequence of bytes, you don't get ones dropped out in the middle. But it turns out Erlang does not guarantee this. Process B can receive M1 followed by M3 without getting M2 in the middle. And we were shocked and appalled. And you see, because we think they know what they're doing. Why does it have this terrible property? So if you look at the informal human language semantics and the formal semantics that people have done, it's both very clear. They do not guarantee reliable messaging, only ordered. So yes, it can happen, and in practice it can happen as well. And in particular, it happens when nodes are disconnected and reconnected. I'll come back to that. So we found another nice paper by other people in the Erlang community. This was presented at the Erlang workshop a couple of years ago. And they were proposing because people had done formal semantics, and they were kind of ugly because they were retro, done after the implementation. So they were looking at what the semantics should be. So they have a formal specification that does guarantee reliable ordered messaging, none of this dropping business, and it has some simplifications in other places. It's more asynchronous, and it's quite nice. The fact that it was just a whole nice thing, we said, okay, brilliant, let's implement that as our semantics. So in a way, we're kind of refining our design principle here from if in doubt, do it, Erlang does it too. If in doubt, do it the way the Erlang people think it ought to have been done, or it ought to be done now, if only they didn't have backwards compatibility problems. So what does this do in this new lovely formal semantics? Well, actually, this doesn't guarantee you anything at all. All these things can happen. These things happen totally asynchronously, and in fact, there's no even ordering between the link and the send. They can happen in either order. So this doesn't guarantee you anything about messages having been received. But if we make a small change, we link, and now we send, now we expect some reply, and then unlink. Now we can guarantee that if we got to, we can guarantee that we'll either get told that the other process died, or we will actually receive a reply. And interesting, it turns out the order in which you say link followed by send doesn't actually matter in this situation. You have to sort of think about it carefully to work it out, but it doesn't. And in fact, the semantics doesn't guarantee that they'll happen in any order either, but it doesn't matter. So it's very asynchronous, and this is sort of slightly confusing, but it does work out. So why does Erlang have this unreliability? Actually, I'm getting close to time, so I might skip on to talk about the status, and if we have time, maybe I'll come back. Because it's a really interesting question, but I want to tell you what the current state of implementation is. There we go, implementation status. So we do cover the full API that was described in the paper. It's very minor changes. We've made a first major release and a few updates, fixing bugs that people reported. We've got a reasonable test suite, and the performance is okay. We've not yet done serious benchmarking. And I would say that it's not yet ready. I wouldn't yet recommend my clients start using it immediately, but it's ready for serious experiments. There's lots of things left to do, bigger scale testing, more benchmarking. There's lots of cool things which I would like other people to do, wish lists for more different kinds of transports, and contributions are welcome, and higher level things like Erlang. A lot of the big thing about Erlang is libraries on top of it. This gen server stuff is hierarchies of processes and monitoring. And there's these libraries that you would need to implement to get that. We have done a little bit of benchmarking. So far, we did some benchmarking at the transport layer, and that we're quite happy with. There's some improvements that could be made, although it's mainly to do with things to do with the IO manager, actually. We have also benchmarked the process layer against the prototype, and the numbers look fantastic. But this is really unfair comparison, really, because the prototype is using synchronous message sending, and we're now probably doing asynchronous message sending. So it's very easy to construct a benchmark where we go enormously faster because we're just sending, if you're at a system where you just send lots and lots of messages and then get one reply later, if you're doing synchronous ones for every single send, that's very slow, and if you're doing asynchronously, that's very fast. So we need to do some proper benchmarks against Erlang. It's all on Hackage. The transport layer is usable by the projects, and the process layers are available. The code is on GitHub, and there's also some documentation on GitHub, not just the API documentation, but how to make sense of the transport layer, for example. So, thank you.
With the microphone.
Ah, yeah, sorry.
That one might be